This short video is about the center of gravity of a system of objects, how you define the center of gravity and how to find it for particular problems. So when we talk about system of objects, what do we mean? Let's suppose we have something like a few cats all running after the same laser pointer, or maybe more realistically, you've got a set of boats all moving on a frictionless surface of a lake, and the boats are all affected by the wind. So when the wind blows, all of them are affected in the same way. We want to generalize this to knowing the effect of like forces on a system of objects. So we say for any number of objects, the acceleration of the system depends on an external force. In other words, the acceleration of a system of objects depends on the total force acting on them divided by the inertia of the system of objects. Well, notice that this acceleration there has the subscript cm, and that stands for center of mass. So we need to be able to find the center of mass of a system of objects in order to know what happens when a force acts on that system. So let's think about how we define the center of mass. The position of the center of mass of some system is defined like this. We'll see a couple of examples and it'll help to understand what's going on. The position of the center of mass is defined relative to some r equals 0 as the inertia of the first one, m1 times r1, plus the inertia of the second one, m2 times r2, etc., for as many objects as you have, divided by the sum of all of the inertias. So m1r1 plus m2r2 plus m3r3, etc., divided by m1 plus m2 plus m3. And r1 and r2 are the positions of each object relative to an origin. Since the derivative of the position is equal to the velocity of the center of mass is going to look very similar to the position center of mass. And sure enough, the velocity of the center of mass is just m1 v1 plus m2 v2 plus m3 v3, etc., divided by m1 plus m2 plus m3, etc. There's actually a fun method of finding the center of mass that we'll try in class, where you can hang an object by one point, like here, and draw a line straight down the object with gravity, and then hang the object by another point, like here, and draw a line straight down the object from that point, and where they cross is the center of mass. All right, so let's do a simple problem. What distance from the center of the Earth is the center of mass of the Earth-Moon system? Let's say this has the Earth as the larger circle and the Moon as the smaller circle. We know the inertia of the Earth and the inertia of the Moon, and the distance between the two is 3.84 times 10 to the 8 meters. Okay, we want to know what distance from the center of the Earth is the center of mass of this system. So let's define our center of mass system as being centered right here where this arrow is, right in the center of the Earth. In other words, the position of the Earth is now 0. So there is no term that has the Earth in it in the numerator. So the position of our center of mass is simply the inertia m sub moon times the position of the Moon divided by me plus mm. And this now, we can plug in values for it, put in the value of the inertia of the Moon, the distance from the Earth to the Moon, in other words, the position of the Moon, divided by the sum of the masses. And we find that it's actually pretty close to the Earth, believe it or not. So the center of mass is 4.66 times 10 to the 6 meters from the center of the Earth. Now this is a more interesting problem. Let's suppose you've got a high school physics teacher who happens to be a hockey team coach. And during a practice, two players are on the ice, right? So they are frictionless. And they are going to now pull on a 10-meter long rope or pole or something like that and pull themselves towards each other by pulling on this pole or rope and sliding on the ice as they move. And then they'll meet at some point, and we would like to determine what distance the 60-kilogram player has moved. Now I'm using the same picture again here, so let's define the 60-kilogram player as the bigger circle and the smaller circle as the 40-kilogram player. And we'll put our 0 position right here at the center of the 60-kilogram player. The thing to know about the physics is that the two players are going to meet at the center of mass. And that is because the center of mass won't move. There is no external force or acting on the center of mass. In fact, we expect the center of mass to be somewhere sort of in the middle of the two objects, closer to the heavier one. All right, so starting over with a simpler picture, we've got let's define x equals 0 as the center of the 60 kilogram player. And where these arrows are meeting is our potential center of mass. And I'm guessing that it's going to be closer to the heavier player. So we start with our expression for center of mass. And then if player 1, M1, is at position 0, then that term will be 0. So we're left with only the position of player 2. And we put in our values for this. We have 40 kilograms as the inertia of player 2 times the distance, the location of player 2, divided by 40 kilograms plus 60 kilograms, and that gives us 400 kilogram meters divided by 100 kilograms, which is 4 meters. So if this was a multiple choice question, the answer would be 4 meters. And that is one slightly confusing but interesting example of using the center of mass.